Swayam Prabha. Digital India. Educated India.
Okay, so let's quickly work out the proof, right? So what is given? We're given two unit speed curves, gamma 1 and gamma 2, right? So let's call gamma 1 is any general point on the first curve. Gamma 2s is another point on the other curve. What is given to us? It's given that both of them have the same signed curvature function, right? So what is it that is given? See what is the signed curvature. You can see here we just derived in terms of the turning angles, right? It's just the derivative. Okay, so let gamma 1, gamma 2 be the two curves with turning angle function. Phi 1 is and phi 2 is. So what is the relation between phi 1 and phi 2 that is given? They have the same signed curvature. Signed curvature is nothing but the first derivative, right? Just give me a minute. Interruption. Okay, so I don't know, maybe time of the day that is working its effect on you guys, but I hope you see that what is given is that the first derivatives of both of these functions have to be the same. Right? Because this is nothing but the signed curvature kappa s. So now, from your school calculus or your calculus first sem course, right? What is the relation between phi 1 and phi 2? Two functions, they have the same derivative everywhere. So can the two functions be different? If yes, then what is the difference?
Sir, they can be different such that they are on different heights of the plane.
Okay, so basically there is a difference in a constant, right?
Yes, sir.
Yes, sir.
So I will just say that phi 1s has to be phi 2s plus some theta. Let's just call that constant theta. Okay. So now, in terms of these turning angle functions, what is the tangent vector? Again, I think and this d gamma by ds, right? That's your tangent. In terms of turning angle, it's just cos of phi s, sine of phi s. So d gamma 1 by ds, that would be cos phi s, cos phi 1s, sine phi 1s. Phi 1 in terms of phi 2, let's replace it, I get phi 2s theta, sine phi 2s plus theta. Okay, so cos a plus b. Anyone?
Cos B minus sin A sin B.
Okay. I really don't remember these things. cos A, cos B minus sin A, sin B. B
Sin A cos B plus cos A sin B.
sin A cos B plus
Cos A sin B.
B sin B. Right. Now we have d gamma 1 by ds, right, on the right hand side. So what is gamma 1s going to be? Because gamma 1 is the curve, right? How do I find gamma 1 given its derivative?
Integrating.
Integrate, right? So let's say I start at some value of s alpha to s cos phi to, let's say, t. Let me write it. So cos theta is a constant. I can already write it outside the integral. 1 to s cos theta minus sin theta. It's also some constant. Alpha to s sin phi to t. Same thing for the y coordinate. Yes. Sin phi to t dt plus sin theta to s cos phi to t dt. Anything else that is missing? Something is missing, isn't it? See, we did more or less the same thing here, isn't it? We are saying the derivatives are equal, so the functions would be different by some arbitrary constant. Here we are doing the same thing, isn't it? When we are integrating, it's a definite integral, then there would be an arbitrary constant, isn't it? Right? That arbitrary constant is nothing but this initial value, right? At alpha. So let me write that arbitrary constant by gamma 1 alpha. You can see that arbitrary constant would itself be a coordinate. There will be one arbitrary constant coming from the x coordinate function and another arbitrary constant coming from the y coordinate function. So both of them written together, I'm just writing it as gamma 1 at alpha.
Sir, but here we are doing definite integral, then why we are adding like?
But we are starting at some arbitrary point, isn't it?
Oh, okay, yes, yes. But well, we have defined earlier, like from alpha to beta.
But the alpha and beta can be anything, right? So it's like given a curve, where is the starting point? You can start from any point on the curve, isn't it? Okay. So now let's just write this in a neat way. right? I hope I've not made any mistakes here. What is this? I mean, this phi 2 is the turning angle, right? Turning angle of the second curve. When you integrate it out, you get its x and y coordinate. So this is nothing but gamma 2s. What is this? Matrix. Are you familiar with this matrix? Anyone? Anyone who is familiar with this matrix?
Sir, I know that its property, its modulus is 1.
Okay. So let's just quickly see what happens when you multiply this matrix to the point 1, 0. This is x axis, this is y axis, this is your origin. This matrix multiplied to the vector 1, 0 will give you what? The cos theta times 1 minus sin theta times 0. So you get cos theta. Similarly, sin theta times 1, cos theta times 0. You get sin theta. So this is nothing but a rotation matrix where the rotation is by an angle theta. Okay? But if you are not familiar with rotation matrices in XY plane, it's okay. Just believe me, this is a rotation matrix. Okay, but you can clearly see what is the relation between gamma 1 and gamma 2. Of gamma 2, and when you add a constant vector to all points, right? Remember, this is the relation we have obtained. Plus, let me write the constant gamma 1 alpha. It's the same. So what does this mean? This is true, this relation is true for all values of S, right? And this constant does not change with S, this matrix remains the same. Which means that I can rotate gamma 2 and then shift the entire curve, and I'll get the curve gamma 1. Right? So if my gamma 1 is gamma 2 is something like this, my gamma 1 could be something like this. Assume that I've drawn it properly. Okay. So I can shift gamma 2 and then rotate it so that I end up with the same curve gamma 1. The importance of this theorem is, if you are trying to, again this is in terms of applications, let's say this is some object in a plane, right? And you want to write an automatic algorithm that recognizes this object. Okay, in let's say new images, right? So in that sense, you can see that if gamma 1 and gamma 2 come from the same object, one way to recognize that they are the same object is maybe to use curvature as a feature. Right? So that's sort of a very practical implication of this. Here, it's okay if you have not followed this derivation exactly, but I hope you get the idea. So I don't know, receiving less response compared to yesterday. Maybe again, as I said, it's the time of the day. But let me move on to what I want to do today. Okay, so is the screen visible now?
Yes, sir.
Yes, sir.
Yes, sir.
So the second part of what I want to do is we have sort of discussed curvature of curves in a plane. Now, so of course, extend what we have been discussing to curvature of surfaces. Okay, begin with, and of course, for now, let's assume we are talking of surfaces of, let's say, our day-to-day objects. Okay, so the surface of the objects can be seen as a subset of our three-dimensional world, right? And our three-dimensional world, we can represent any point of this using its x, y, and z coordinates. So this collection of three coordinates is what I'm going to sort of denote here by this symbol R3. I'm not sure if you have been taught what does this mean, but for now you can just think of it as a collection of three real numbers where each three real number, they represent the x, y, and z coordinate of a point. So surfaces of objects can be therefore considered as a subset, right? So now the question is, we've seen that curvature of curves, they measure the deviation from a straight line, right? That part was quite intuitive, and all of you followed and you agree with me. Then the curvature of a surface, right? It also measures deviation, but from what?
A plane.
Plane, right? If the surface is flat, we say it's not curved, right? So therefore, the surface is flat is 0. So trying to come up with a measure, okay, which captures how much a surface deviates from being a plane. Okay, and again, analogous to the examples that we gave for curves, if I have a plane, you would say curvature should be 0. If I have a small sphere, okay, again, when I say sphere, I am looking only at the surface of the sphere. Don't consider the volume properties here. Okay? Only points lying on the surface of the sphere. If I take a small sphere and a large sphere, which of these two surfaces would have a higher curvature?
Smaller one.
Smaller one.
Smaller, right? Good. Higher curvature. Okay, so this is what we are going to work with. The intuition is this, and whatever mathematical equations or formulations we derive, they should sort of match our intuition. Okay, right. So the first thing is, since we have already done so much work like measuring how curved a curve is, can we just reuse this in order to quantify the curvature of a surface? Okay, so let's say this is a surface in 3D, X, Y, and Z, right? So this is a surface. Let's take any arbitrary point P on this surface that I am denoting with capital S. Now, as you can see, I can sort of draw several curves on this surface, right? The curves entirely lie on the surface, but they pass through the point P. Okay, so example, this, so on and so forth. Okay, all these curves, let's say gamma 1, gamma 2, gamma 3, gamma 4, and infinitely many more. Right? Each of the curve we already know how to measure its curvature. So can I use this collection of curvatures in order to capture how curved the surface is at that point P? Again, I sort of forgot to mention this point, but again, curvature even for a surface is a local property, right? The curvature at this point of the surface and this point of the surface may be completely different. So it's a local property, and what I'm trying to say is, can I just use curves? The only change now is that the curves should entirely lie on the surface, and they pass through the point where we are trying to capture the curvature of the surface. Okay, so that's going to be our first attempt. Okay, so to measure curvature of the surface at a point P, we are going to first see how to summarize or capture curvatures of all curves on the surfaces that pass through the point P. Clear? So it's not as easy as it sounds. So intuitively, curvature of a curve, as we have seen, it measures the deviation from a straight line, right? What would be a straight line on a surface? Is the question understood? So if I
Can
take
you
this
please brief it?
once again.
Yes, sir.
Okay, so what I'm trying to say is this method in order to study curvature of a surface at a point, right? Let's use curvature of all curves that pass through this point, and these curves entirely lie on the surface. In order to do that, there is one issue that will arise. The issue is, if we try to capture curvature of a curve, we've already seen it captures this idea that how much the curve deviates from being a straight line. Now, if we try to capture the curvature of curves on the surface, is it fair to do that? Simply because if the surface is curved, right, the first question is, can we have a straight line on a surface? You're measuring deviation of something from an ideal thing, but that ideal thing, is it possible to have that ideal thing on the surface? Anyone? Can we have a straight line? So let's just take a simple example. Right, our Earth, let's assume it's a sphere. Right, this point and this point. Right? In our day-to-day language, you always use this terminology, right? If somebody asks, we sort of say go straight. Okay? But remember, you're living on the surface of a sphere. So what does it mean to go straight on this surface? Does that make sense?
So does it mean that we have to travel parallel to the curvature? Matlab, if we travel with the same curvature as the sphere, then we are moving in a straight line.
So what does that mean? I mean, so curvature of a sphere is something we have not yet characterized, right? In fact, we are trying to do that by first figuring out how to measure curvature of curves. And as I said, the first difficulty is, can we have a straight line? Right? So how do you characterize a straight line on a plane? We say a curve is a straight line if curvature is 0, right? At all points, of course. Is that going to be possible? So on a sphere, what would be a straight line?
Sir, maybe we could take the difference between the curvature of the line and the plane and make that 0.
Difference between curvature of a line and a plane. But again, if you intuitively agree that curvature of a surface should measure deviation from a plane, that means you have already accepted that curvature of a plane is 0.
No, sir, but the curvature of the plane might not be 0 because here the line which is a straight line in spherical plane might not be the straight line in
So, just
planar
sorry
plane.
for interruption. What do you mean by spherical plane?
Here the plane we considered is the surface of the sphere. So usually the plane we
Oh,
consider
okay. By
flat.
plane, I mean the usual XY plane or something like that. That is what I would call plane. This thing I wouldn't call it a plane. It's a surface of a sphere, right?
Yes.
So now go ahead.
So the straight line so the line which we are drawing here
Mhm.
between P and Q, let's suppose,
Okay.
that might be a straight line with respect to the spherical surface, but not with respect to the flat plane.
Okay. So, but then you can have several curves, right? Several lines.
Yes.
Which of them is straight and which of them is not? There are infinitely many. I can sort of go the opposite way, come back here. Okay, so you see, I mean, yes, I don't expect you to answer this question, but you can see that you will not have the usual straight line that we are familiar with on a plane on a general surface. At least that much you agree?
Sir,
Yes, sir.
can we go infinitesimally small and uh, take a very small part, and then we will take a tangent to it and measure as play means curves in 2D.
2D. So once again, so let's say I take this point, say A, take a tangent to the sphere here, then
Then we can assume it as a plane surface, as means we used to do that. If we take a very infinitesimally small part, then we can assume it as a plane. You have drawn left side flat plane.
right, but in that sense, then every curve becomes a straight line. You can break this curve down into as small fragments as you want.
So can we apply the same definition over here, like the shortest path between 2 points? If that is taken on any surface, that would be a straight line.
So thank you. What's your name?
Ishan, Ishan.
Ishan, right. So that's another property, right? Or so straight line of a plane, it has two properties. One, curvature has to be 0, right? The second property of straight line on the plane is it is the shortest path between its endpoints. right? So, but both of these are the same as far as the plane is concerned, isn't it? So let's try to sort of tackle both these issues. One is basically the way you have defined curvature, you're never going to have a curve which has zero curvature. Right? I mean, I'm talking of a general surface. Of course, if your surface is flat, then yes, you will have, but in general, you'll never have a surface which is flat, and therefore you cannot expect to have a curve which has zero curvature at all points. Okay, so that property, and on the plane they are connected, they are also connected on a surface. So that is the main aim behind today's class. So let's sort of go a little forward here. Okay.